Right, so I want to go through another change that I've made to this. The primary change in this is just in the camera movement. So it's effectively the same stuff before plus water, and a little bit of coloration changes to the materials. So let's start getting into what these changes are, particularly for how did we make the camera move. All right, so I'm going to pause this. Well, whatever, we'll just let it run in the background. So over here, I have a camera root, and I guess I will pause it now. And let's go take a look at the camera root. It's right over there. And the actual camera above. There it is. So to get both in the picture, it's these two spots here. All right. So main camera, this is of course the actual camera. It does not have a script on it. Camera root does. Camera root, one really easy thing to think about when you're trying to control a camera, you don't have to use just one game object. You can do all of the mathematics to solve it on your own, but quite frankly, a lot of the solutions to this come out pretty straightforward when you start to simplify things down to a couple layers of game objects or a couple layers of transforms. So the first transform is just moving its position around to kind of follow what we're doing for work. So if I unpause this and go to the scene view, you can see it's following where the work is. So it has a lerp motion to move itself towards there at a speed that's not as fast as that one, because if I matched its speed, which is closer to like 60, then we see the camera is very jittery. And if I move that over, close your eyes if this might make you sick, everything moves around really fast, and that does not work well. So we go back down to 0.5. There. And this now allows it to move relatively smoothly as that continues to make changes. Okay, anyway, so we've got this object that's following it around, and then that kind of explains a little bit about our time lerp to target. But then we also have rotation time, because it's rotating as well, and it's got a certain amount of time that it can rotate around. And if I go back to the game view, this will make the most sense for it. So one thing is, it's going to take anywhere from 3 to 8 seconds to complete this. To make this next part stand out, or the next explanation stand out, I'm going to reduce these to 1 and 1. This means that its rotation will move quickly from one spot to the next. Now that is a pretty fast movement when it's moving around 180 degrees. But otherwise, actually, let's just move it to 2. But you can see that right as it's getting to the end of where it stops, it comes to a smooth stop, or it comes to a point where it kind of comes to a stop and then smoothly picks its speed back up. And that's because of what we would think is a slurp operation, but it still basically is. But instead I'm using an animation curve. I couldn't find a slurp function inside of the mathf or the vector lerping, so I'm assuming it's still there. I'm somehow missing it. Anyway, so inside of this code, I am now using a curve instead. So you see how it's kind of smooth and how it transitions from one point to the next. If I were to switch to this would be a transition that immediately changes speed from one speed to the next. So as soon as it gets to the camera point where it relaxes its rotation, it immediately starts moving at the same speed in whatever direction, or moving at the same amount of time it would take to reach the next target, next rotational target in 1 second or 2 seconds. Anyway, but I don't want that snap movement, so I threw in this animation curve. And I'll show you how to use that in a minute if you haven't seen it. All right, so let's dive in and start taking a look at the actual code here. Okay, to begin with, it was primarily in camera tracking. However, camera tracking now is that center point. It's controlling the center point, the target that everything else is going to pay attention to. It used to be that this was inside of GroundBot. And then ForestBot was paying attention to GroundBot as well. And GroundBot was also controlling the camera. But when I switched this over, the camera became more about the center point or the central control point. And then GroundBot is influencing that. All right. So now let's move on a little farther into the code. Well, actually, since everything is reference needs to this, I created a singleton reference out of this. Now I've got the camera object that I need to pay attention to, and of course the target that I just talked about. Now inside of here, we've got a value for how long it takes us to lerp to whatever the target position is. And so far I've been finding 0.5 tends to work about the best for what we've been doing inside of this so far, so I'm going to set the default there. The minimum rotation time, it seems like larger numbers tend to work better, so I'm going to go with, say, 3 and 8, because that's what I've ended up changing things to. Now, these other floats are private, but we'll go a little bit farther into what they handle when we get to the math. Actually, no, I'll explain it now. Original rotation. This is where our rotation started. So basically, when we're doing this now, we're going to be using a lerp function where we need the original and the target rotation. So I want to know the original rotation and target rotation as we move from one point of rotation to another. I also want to know how long it's going to take to make that rotation, and I need to know a rotation counter. I need to understand how much time has passed since we started our rotation. And of course, also the animation curve. I guess this would make more sense to drag up here. There. All right, next in the start, the first thing that we do is just take the camera object and tell it to look at this. This is the root object. It is going to be the focus point of what that camera does. Now, nothing else is going to move the camera. So no matter what I do, if I move this object or I rotate this object, the camera will move right along with it in an equal amount or necessary amount so that its rotation will still be pointed at this object. All right, so we effectively only need to look at it once. Next, we call the set next rotation because that effectively initializes this. Okay, so from here, we're going to get the original rotation, which is basically just the Euler angles y. Then we're going to get the target rotation, which is just getting a random range between 0 and 360. Then we're going to set our rotation counter back to 0. This is basically how much time in seconds have passed. Then we're going to take our time for rotation and establish how long we can move for this one. All right, so within this, that's basically just the minimum and maximum rotation, just grabbing a number between there. Now for the last part, which this entire function or this entire class only took about 55 lines. First thing we're going to do is take our camera, and just like the GroundBot did, we are lerping over to where that is. We are doing this in the same operational style where we're taking the transform position wherever we currently are and moving it over towards the target position. So as the target position moves, we start moving toward it. If we are keeping our transition, our lerp, in a slower speed or a smaller number, then that transition appears more gradual and we don't see the change that happens in this, because let's pretend that we are at 0.1. Or actually 0.5 works great. We are at 0.5. So let's just say that our lerp of 0.5 matters. Now there's more to it because we also are multiplied by delta time. But let's just exclude that one and just say that this is per frame. Okay, so we've got our transform position. That's where we are, and we want to get to the target position. So we are basically lerping towards that, and we are saying, let's lerp towards that at time to lerp to target. So let's just say 0.5. That means that it's going to move us halfway from position to target. So if we were 100 meters away from it, or let's say we were 40 meters away from it, this will return us 20 meters away from it. And then if we run it again, 50% of 20 is going to be 10. 50% of that is 5. 50% of that is 2.5. 50% of that is 1.25. So this, you can start to see it's gradually slowing down. It'll never quite reach 0, except for the fact that the resolution of this of a float is finite, so we run out of space and still effectively get to zero, or some other. I don't know if it runs into an infinite or some other error on that. I don't think I've ever tried. Anyway, so we got time to lerp, and then basically this moves us towards there. So we want to just find this smooth speed operation where like 0.5 moves us there nicely. Okay, so anyway, we're just moving our way over to that. Next, we got the rotate. We are going to rotate the camera, and this one has a lot more to it. If we just wanted it to move smoothly at a speed, we could just grab the Euler angles and then add time.delta time to the y value, and then put that back, and that would be it. That's all we need to do if we just spun in a circle. But I find that if we are changing it as we are building all this stuff dynamically and moving around randomly, it makes it feel more like the camera movements are purposeful, like they have more meaning. Now, they are meaningful in the sense that they let us continue to see what's going on, where it's working, where it's putting things. Anyway, but yeah, so we're getting that. We're basically just increasing how much time we've taken to start this operation, and we're going to divide that by the time for rotation. So we're at the beginning, we're 0. 0 divided by, let's say it's 2. And then we move on, and let's say that the next time we get up to here and we're 0.5. So divided by 2 means that we're going to be at or what would that be? 12 point, it'd be 0.125, 125. Anyway, and then once we say that we are at 1, we're going to be at 0.5. That's the numbers it'll get back to us. So if it's the actual, once we get up to the final time for rotation, then the value we're going to get is going to be 1. Okay, so, and we're clamping it between, with the clamp 0, 1 function, which is a nice alteration because a lot of functions we want a value between 0 and 1, and we have to add these if statements that are checking to make sure we didn't break over it. Otherwise, we might get negative numbers or numbers greater than 1. Okay, so moving on. If I ended up taking that number as it was, as soon as it reached the end of its rotation, it would be moving at a stable speed the entire time. And then once it chooses a next rotation, it would immediately start moving at a stable speed to the next rotational target. But that point of transition means that it was going to be a jarring transition. So effectively, I'm running it through this rotation strength curve, which is this animation curve here. I'm going to pause that because that gets a little choppy when I have this thing open. Anyway, so that'd be like running it this way. 0 is 0, 0.1 is 0.1, 0.9 is 0.9, 0.5 is 0.5, 1 is 1. This way, of course, as we saw before, changes gradually. 0.5 is still right in the middle. 0.5 gives us 0.5. 1 gives us 1, and 0 gives us 0. But until we get out to like 0.5 or something, sorry, 0.05 or 0.1, we're still pretty close to 0. We're going to be at like 0.004 or whatever. I don't know what the number would be. But we get this slope here, a smooth transition. So it starts off not moving very much and then starts going into a faster speed. And then as it gets to the end, it starts coming to an end because it almost reaches everything it needs to get to the end by the time it's gotten to about 0.9 or 0.95. Okay, so this gives us a new time number out of it. We're basically smoothing this out, but we could use whatever function we want. All right, so now we're going to say that the rotation is going to, the angle that we want to be is going to be between our original rotation and our target rotation, and passing in that time from the curve. So now that we have our rotation value, that's the angle, what angle we're going to be at. So it could be anywhere from 0 to 360. We're going to set that for the Euler angles y and then pass that back into the Euler angles. And of course, if the rotation counter the time tracker that we're keeping is greater than the time that we allot for rotation, we are going to set the next rotation. And that's it. There was one other thing. We added water as well, and I changed and smoothed out a little bit of the numbers on all of the coloring. So I'm going to unpause this. And one thing that I did is that when we are inside of the solid objects, I decreased the smoothness. So before it was a 0.5, which you can see is like shinier and we get reflections off the grass. That doesn't work as well. But if I have this lower, we can still see the light has a little bit greater of an effect on it, but not that much. And then the water, I added water to this. The water over here has a much higher reflectiveness or smoothness that comes out to show that even more. So we end up getting like sharper lights and reflections showing off of it. All right. I believe that was everything that's in this. Oh, the other objects that are in here, like GroundBot, we're now having to use camera tracking.instance.target to get the position where this used to need the position. And same thing in ForestBot. It's doing the same thing here where it needed both of those. All right, and as usual, this code will be available on GitHub. The link is in the description, including the commit for this specific change. All right, hope you found this useful. I'll talk to you later.